Okay, problem 7 says estimate the number of photons emitted per second by a 15-watt fluorescent lamp. Hint, take an average wavelength. So let's just start off with that hint. And for our average wavelength, we will take green light, which has an average wavelength of about 500 nanometers, which is pretty much right smack dab in the middle of the optical spectrum. Okay, and so once we have that, we now want to find the energy that a single green photon would have. So the photon energy equation is given by E. Energy is equal to hf, where h is Planck's constant, f is the frequency. We as well could plug in our equation f is equal to c over lambda, which we've used earlier, to get the energy as it relates, instead of to frequency, as it relates to the speed of light and the wavelength. So E is equal to Planck's constant times the speed of light divided by the wavelength. And so with this, let us find the energy of a photon which has a wavelength of 500 nanometers. So this is going to be Planck's constant, 6.6 times 10 to the negative 34 joules seconds, times the speed of light, which is, of course, 3 times 10 to the 8 meters per second, divided by our wavelength, which is 500 nanometers. So nano is times 10 to the negative 9 meters. And we ultimately end up with a wavelength, or an energy for 500 nanometer wavelength photons of about 3.96 times 10 to the negative 19 joules. And like I said, this is per photon, which I'm tacking on the per photon. It, of course, does not come out of this equation necessarily, but we know that that is the energy per photon. Okay, and so if we have a fluorescent lamp that outputs 15 watts, if we divide that by the energy of a single photon, what you'll see is we'll end up getting the number of photons per second, because watts, of course, are just joules per second. It's energy per second. By dividing by this energy per photon, 3.96 times 10 to the negative 19 joule per photon, we get that the joules will cancel out, and we will have 1 over photon, which will pop that up, and we'll have photons per second as our units, which is exactly what we're looking for. We could also call this N, right? The number of photons. So 15 joules per second divided by 3.96 times 10 to the negative 19 joules per photon will give us roughly 3.79 times 10 to the 19 photons per second. And these are the photons per second that are emitted by this 15-watt fluorescent lamp. And that does it for problem 7.